So I can just start off my presentation, Sumit.
Yes.
So I think
Could you change the view of this presentation?
yes, just a second. I'll let you.
Can we put it in the view mode, please?
Just a second. Can we see the presentations,
Not yet,
Sumit?
not yet, not yet.
So can you share from from your
I'll
side?
do that. I'll do that. I'll
Yes,
do
please
that.
do it.
Let me
I
do
can't
that.
get there is some requirement from.
Okay. So
Great, I can see.
let me just
So to start with, let me give a brief idea of what the last two sessions were. I'm representing Drive. I'm the Chief Technology Officer of the Delhi Science and Technology Cluster under the August Office of the Principal Scientific Advisor to the Government of India. And essentially, I'm a semiconductor and IC design engineer, essentially an analog IC designer, which who has spent more than 15 years in industries, including Intel and ST Microelectronics, and in the later phase in the government defense labs before joining this science and technology cluster. So, as we have already mentioned, one of our key mandates is to promote the government policies in the deep tech, and one of them is also about the semiconductors. Apart from semiconductors, we also deal with artificial intelligence, we deal with quantum computing, and so forth. But right now, we are focusing on semiconductors because semiconductor is a very growing market, and essentially, this is one of the markets. Which is the foundation of all the other fields. So the semiconductor industry is when I say semiconductor industry is the foundation, it means that the other industries, the high tech industries, whether it be the electric vehicle industry, EV industry, AI, quantum computing, and other industries, they are all fueled by the ICs, which fall under this particular semiconductor industry. Ironically, India has been a very hot destination of IC designers. We have a great pool of more than 20 or 25,000 good designers, both in analog and digital field. But we are not doing so good when it comes to the manufacturing aspect of semiconductors as well as the electronics. So our import bills are rising rapidly, and with the present hostile international environment, we wish to be self-reliant in these critical technology areas. So, Government of India has launched programs specifically for the manufacturing activity in semiconductors. It is called Semiconductor Mission, uh, through which we plan to develop an entire ecosystem which will not only make India a very self-reliant country in these critical technologies, but will also create jobs for our youths, and those jobs will be very meaningful and satisfying white-collar jobs, uh, uh, which will be which will not add which will not put India on the global map of technologies, but in fact we wish to lead this particular race. Let me start my presentation in a more formal way. So why this topic now? Obviously, as I said, that the growing demand of the semiconductor products. And when I say semiconductor products, it not only makes ICs, but semiconductor product also includes advanced materials. So we deal with high quality silicon, we deal with high quality gallium nitride, GaN, we deal with GASIC, gallium arsenide devices, indium phosphide devices. So these kind of materials also fall in the category of semiconductor field. So there is a misnomer that only electronic and electrical engineers are welcomed in this field. This is not so. We also require people from metallurgy background. We require people from chemical background. We require people from mechanical background, and obviously people from electrical, electronics, and computer sciences. We have role for every traditional engineering field because semiconductors is a very interdisciplinary area. And the courses which we plan to launch is all about manufacturing. Is It's not only will be limited to the design aspect. Obviously the design aspects will be taught, but such courses are running by multiple agencies, multiple IITs. So there is nothing much to add to what is already in the market. What we plan to do, and this is as per the mandate of the government, and we have taken also inputs from our industrial partners, including top companies like Cadence, like Micron, like Anritsu, and others, that what should be done, what skills should be imparted to the budding engineers or even the working engineers who wish to upscale and take a different field, what skills should be imparted. And based on their inputs, we have come to the conclusion that we should be taking this particular I should, or at least at this point of time, I should be talking in terms of why and how it should be done. So the growing demand from the artificial intelligence, you have seen how chat gpt and other such applications are working, but on the back of it, you must be knowing that GPUs, that is the graphical processing units, are playing the key roles. And again, the GPUs are a part of the semiconductor business. So they are the those specific ASIC application specific ICs, ASIC ICs, which are made again not in India, and we are heavily dependent on it. In fact, only one or two companies, Nvidia and AMD, have a kind of a monopoly on it. So someday we plan to have our own GPU system in India, getting manufactured here in India, so that we are not dependent on any other country for our AI, 5G, and other needs, because this is going to play a critical role in the development of our nation. So, growing demand from AI, 5G, and automotive industry. Then now we are figuring out that Moore's law. So this Moore's law is the basic of the semiconductor industry, which says that every 5 years the number of transistors or active device on an IC gets doubled. So for the last just 30 for around 50 years, this law has proven to be correct. But now with time, we are facing some kind of a limitation in terms of power integrity, in terms of packing density, in terms of maintaining the form factor and other such things, that a new way of handling semiconductor products or designing and manufacturing semiconductor products has become the need of the hour. So Moore's law is obviously still applicable, but it is showing some kind of a saturation. So we are figuring out how to bypass this particular limitations and still continue with the growth of the semiconductor high speed systems. Third, we wish to tell you how so the second and the third is the same of the Moore's law and how to bypass it. The third is a kind of a heterogeneous integration and 3D packaging. This particular masterclass or webinar and is the future, and the following skilling programs will be more about this kind of a unique uh, uh, imparting this kind of a unique skilling and the knowledge base to the participants, in which these kind of in 3D packaging and and heterogeneous integration of ICs will be taught. And not only will be taught, but the participants will have a first-hand experience of how those kind of products which have these components function and can be used in the industry. Sumiti, just the next slide. Yeah. So just going through the basic definitions, as I just said that Moore's law has to be, the limitations of Moore's law has to be tackled, and we are figuring out some methodologies of without breaking Moore's law or without inventing any other law, how to still ensure that the progress of semiconductor ICs and semiconductor products uh, uh, is achieved in the similar fashion what we have seen in the last 30 years. So some of the concepts which have come to the fore and the last 10 or 15 years, they have proven very right. They are, some of them are called heterogeneous integration. So when you have a different kind of ICs, like you have a memory IC based on NAND, you have some ICs based on flash, DRAMs, DDRAMs, and you are running a system which also includes some kind of logic devices, and you have to integrate it. So the heterogeneous integration concept comes into play, because heterogeneous here says that different kind of ICs. So one is having memory, one the one of one IC number one may be having a role of a memory device, the IC number two may be a logic device, and both have to speak to each other. So both have to communicate with each other. So what kind of system integration approach we need to take, and that says about the heterogeneous integration, of how to put it in a single package. Now again, 3D packaging. So heterogeneous integration, when I say, it can be planar, so ICs can be side by side. But when I come to 3D packaging, 3D packaging is a special subset of heterogeneous integration, in which the ICs are placed one above each other, so stacked or vertical. And we do such kind of placement, routing, and floor planning, that the whole system becomes absolutely flawless. So when the IC1 interconnects and talks to IC number 2 or 3, there is no glitch at all. They will function as if they are functioning independently, although they will be sitting just above each other, and will be connected through connects, which will just see they will be called through silicon wires, TSVs. So this 3D packaging is just a special case of heterogeneous integration, in which we are bringing a lot of different ICs and combining it together. So the whole idea is to make everything miniaturized. It has different advantages, but also has got a lot of challenges, which we will be looking uh, in some time. I just saw a message from some member asking for kind of a uh, software required for these kind of things. So there are companies, various EDA tool companies, so including Cadence, including Synopsys, including Ansys. They have got different kind of the proprietary softwares which are used for these kind of integration. Like, for example, as most of you know, Virtuoso or Analog Design and Environment, ADE, are the proprietary software of Cadence. In a similar way, ANSYS has got its own tools which does these kind of floor planning and does these kind of integrations. So the next slide. So yeah, so this is a visual depiction of what I just told our participants, that when we go for heterogeneous integration and 3D packaging and chiplet packaging, these are how we interconnect them. So bumping and interconnection. So bumping is a sort of you can say small nodes or small dots, and an array of small dots made up of either copper or the alloy of copper and silver, CuAg, which increases its conductivity. And on top of those bumps will sit our chiplets and or the pads. And then we do some kind of soldering, ultraviolet, ultrasonic soldering, to join the various ICs. So these are some of the ways in which we do the integration and soldering. So if you can see, there are a lot of different components. This is what we were so I was saying when I said that heterogeneous integration. So you can see in one single system, we have antenna, we have sensors, MEMS based sensors. MEMS are essentially sensors and actuators. These are the special category ICs which have mechanical elements ingrained in it. As you can also see, we have silicon photonic devices are now very common, because instead of electrical signals, they use the specific wavelength photonic signals, which increases the speed and hence increases the bandwidth of our product. So next slide, Energy. Right. So this is a very zoomed in version of what you just saw. You can just see how we have put various different kind of my ICs. So this is a depiction of the heterogeneous integration and in a 3D format. So this is a 3D packaging. So the devices are packed in a 3D, so XYZ format. So the devices are stacked one above each other, and since devices are of different natures with different functionalities, so the difference in functionality makes them heterogeneous, and the way they are positioned on each other makes them 3D. So this is a heterogeneous integration in a 3D fashion of my packaging. So here you can see DRAM core is there on the top, memory devices is on top. It can be even at the bottom also, but here I have depicted in a on the topmost top part. You see the bottom part is the read and write logic circuitries. So the read and write logic circuitries can be differential amplifiers or operational amplifiers. So in a way, they are the analog devices or analog ICs which are at the bottom. Then you can see the IO buffers. IO buffers are again, if some of our students are from the electrical background, they are simply the op amps connected in a special fashion so that there is a kind of an isolation between the power rail lines bit of the input and output circuitry. So we have uh, IO buffers, we have IO pads, we have DRAMs, we have read and write logic circuits, and so this is an amalgamation of different kind of ICs, so it makes it heterogeneous, and these ICs are put one above each other. So it makes it a 3D representation, and they are connected through a through silicon wire. So these silicon wires are special kind of a very finely drilled wires. Those drilling are done either in a very sophisticated laser way, and then they are filled with either high purity copper or copper and silver amalgamated alloy. So this is how the packagings are done for the highly complex subsystems. Next presentation slide, please. Yeah, so this is the technologies in which I was just explaining. The HI stands for heterogeneous integration, and 3D packaging is the representation. So how we have connected these things. So TSV stands for through silicon wire. Through silicon means the different layer of silicons have been punched through laser beams, those are very fine quality. So the diameter never crosses 20 micron width. So that is the level of accuracy we need to maintain. And then we have micro bumps. That is these semicircular array of semicircular alloys on which we place our ICs and wafers, and we do some kind of a soldering. So that is called micro bumps. And hybrid bonding means the bonding is a mixture of TSV, microbumps, and the traditional line wiring. So these kind of technologies we generally use for packaging, the modern packaging. Silicon imposers are the intermediate layers. They are made of either of the high quality glass or silica, or even the ceramics, or doped silicon. These imposers are used as an intermediate layer for stacking multiple different ICs in a horizontal pattern. So these are the kind of layers on which different different ICs, logic ICs, memory ICs, and other IO ICs, they will be stacked next to each other, not in a 3D fashion, but next to each other. So this falls under HI categories. So again, the wafer level packaging is again a special kind of packaging. In fact, one of the special kind of packaging is also called chip on wafer. This is a TSMC proprietary technology, and which is you can see CoWoS. That is also, so CoWoS is a type of technology which was formulated by TSMC, Taiwan's Semiconductor Manufacturing Corporation. Foveros is by Intel, and similarly in Info is from AMD. So these are the different kind of packaging technologies in which they use different kind of materials, but essentially the architecture is the same. The idea of having different kind of technologies is mainly commercial, but apart from commercial, they also adheres to different kind of user case. So, for example, CoWoS is a TSMC. TSMC is essentially into memory and analog IC design. So, in that case, their user demand is different. So, the kind of materials they use is a little different. Foveros is essentially given by Intel, which is into the manufacturing of CPUs, central processing units. So they have a very specific demand in terms of, say, speed, latency, power management. So they have a very different set of materials which they use for their own integration. So these are the different types of integration which different companies use as per their R&D and also as per their end users. Next slide, please. So